Hi there. In this video we're going to look at how we find the volume of a sphere. We're going to look at how we derive the formula. So our strategy is going to be to look at this hemisphere. Now it just turns out that the maths is slightly easier with a hemisphere than with a full sphere. And that doesn't matter because we can just double it at the end. But we're going to start out with this hemisphere. We're going to chop it, as with a lot of these derivations, into lots and lots of thin slices. We're going to work out the volume of each of those slices, and then we're going to make all the slices really thin, and then the limit as their thinness approaches 0 will become a better and better approximation to the volume of the hemisphere, and in the limiting case it'll actually be exactly equal to the volume of the hemisphere. So let's get to it. Okay, so we said that our first step was to chop it into discs and calculate the volume of each of the discs. So what we're going to do is we're going to assume that the radius of the whole sphere is r, and the volume of the disc, the disc that we're splitting it up and that we're working out is x centimetres above the base of the hemisphere. And we're going to call the width of the disc delta x because it's in the x direction. As we make that thinner, it's going to have an effect on how many x's we need to do. But given all that information, we should be able to work out what the volume of this disc is. So let's work out the volume of disc. Okay, so well, this disc is a cylinder. So what we need to do, and the volume of the disc is equal to the area of the circular face times by that width delta x. So really what we need to do is work out the area of the circular face. Now remember, the area of a circle is pi times by the radius squared, which means we need to work out what this radius is. Now, to work out what the radius is of the disc, that is, I might just say RD for our disc. We need to work out what the radius of the disc is. What we're actually going to do is use a little bit of Pythagoras' theorem. So if you look here, what we have, and I might just draw this out again to make it really obvious, is we have a right angled triangle here, and that is x tall. And the hypotenuse is r, and this length here is the radius of the disc that we're trying to work out. So using Pythagoras' theorem, we get r squared is equal to x squared plus rd squared, and it's a really simple rearrangement to just subtract the x squared from both sides. So r squared take away x squared. Okay, so now if I wanted to find rd, the radius of the disc on its own, I could square root both sides, but actually, because in our formula we want r squared, it's easy to just leave it in this form. So substituting that into this formula, we get that's equal to pi times by this guy squared, r squared minus x squared, times by this delta x that we're after the width of the disc. Okay, now we'll do a little bit of tidying up of that in the next step, but I think that's actually quite a nice, concise way to leave it just for now. And so on to our next step, which is adding up the volumes of each of these discs. Okay, so we've just figured out that the volume of one of the discs is pi times by r squared minus x squared times by delta x, and now we need to add all of those up. So again, what we get is the volume of the sphere, I'll just call that V, is equal to the sum of all of these discs. Okay, and that is from x is equal to 0. If we start right at the bottom, the distance up is 0, and that goes all the way up to x being equal to that r, or r minus delta x, but in the limiting case it'll be the same. Okay, that's the volume is approximately equal to that, but then as we take the limit, it will become exactly equal to. So what we'll do is we'll take the limit as delta x tends to 0. And you recall from the other video we did where we found the volume of a pyramid, that the limiting case, when delta x goes to 0, just turns into the integral, and that's sort of how we define an integral. So the volume is equal to the integral now, from x equals 0 to r of pi, r squared minus x squared, and then this delta x goes to a dx. We can't just say that this is equal to 0 because we're adding up lots of them. It's a limiting case, it's not actually equal to 0. But yeah, then we can just integrate this guy, and we should get ourselves the answer that we're after. Cool, so in a second we'll move on to actually finding the integral of this. It's not too tricky. Okay, so now we're going to integrate this guy, and there's a few things there's certainly one thing we can do straight away that's going to make this a little bit easier, and because this pi is a constant, we can factorise it out almost to the front of this integral. So integrating pi times by some function of x is the same as doing pi times by the integral of that function of x. It's the same. So then we get r squared minus x squared dx. And then we can integrate this quite nicely. So if we've got the sum of two functions in an integral, we can just integrate them one by one, and then that's going to give me my answer. So the sum of r, or the integral of r squared, with respect to x. Well, r doesn't depend on x. X varies from 0 to r, but r doesn't change once we've set our sphere in place. So that's not a function of x. So this is going to give me x r squared. And then when I integrate this, well, the integral of x squared, we add 1 to the power, x cubed, and then divide by the new power, 3. And that's going to go from 0 to r. So then finally we just need to substitute in r and 0. And this is exactly the moment where we see why doing a hemisphere makes the maths ever so slightly easier, because when we substitute in 0, both of these terms just disappear, the whole thing disappears, so really the only thing we need to substitute in is r. So then we get that's equal to pi times by, well, r times r squared, and what I'll do is I'll just put the ones we're substituting in purple so you can see the difference. So we're going to get r, lots of r squared, and then we subtract r cubed over 3. So now we can simplify that down. So we get pi, well, r times r squared is just r cubed. And what I'll do here is, instead of saying r cubed over 3, I'm going to subtract a third of r cubed. That's exactly the same. R cubed divided by 3, the same as a third of r cubed. Well, r cubed minus a third of r cubed is 2/3 r cubed. So we get 2/3 r cubed, or pi r cubed. Okay, so you might be thinking, well, that's not the volume of a sphere. Where have we gone wrong? Actually, we've not gone wrong anywhere. Remember, this is the volume of a hemisphere. So the volume of a sphere is just double this, and now double 2/3 pi r cubed is what we're after, 4/3 pi r cubed. There we go. So if you're a bit familiar with integration, hopefully that's interesting. Might even be able to go on and try doing some of this with some different shapes. If you're just doing GCSE maths, that's absolutely fine, because this is the sort of thing you can look forward to if you take on A-level maths. This is the sort of thing we can do with the calculus that you'll learn there. And so if you did manage to follow along with that, good job, because it's not easy, particularly setting up the problem. But well done, it's good.